Everyone, welcome back. Our final presenter this evening for the Phase 1 mapping project is Michal Nemčok. Michal is a global expert in tectonics, and he may be a very familiar name to any structural geologist out there. He has written extensively and is the author of multiple books, and I'm delighted that I'm a co-author on his latest endeavor. He's going to talk today about Project InnerSpace's in-situ stress mapping project. And this follows on nicely from the work that Paul showcased just in the previous presentation. So without further ado, Michal, take it away. Thank you.
Hello, everybody. I'm representing this study in this tectonic portion of Phase 1 of Project InnerSpace. To give you a quick intro, if you think about geothermal systems, they require presence of effective play concept elements. We can list them: heat source, fluid source, reservoir, caprock, migration. They are described in detail in a book by Nemčok in 2016, but we can simplify it. They simply interact, and the weaker ones, the impact of weaker ones could be balanced by impact of stronger ones. A geothermal exploration focus on their understanding at geothermal field scale should start with a regional exploration. It is regional exploration that defines the tectonic setting, which controls character, existence or non-existence of play concept elements. So our study uses several inputs. Its input, which was described by Paul just before me, and its second input is a database from a world stress map. We are looking at a global snapshot, and you can see in situ stresses, two perpendicular ones. Color coding defines type of data which were used, whether it was earthquakes or methods applied in boreholes. Knowledge of present-day tectonic stress is essential for numerous applications in geothermal exploration and production, and it includes risking the magnitude and location of induced seismicity, or improving the stability of boreholes, or enhancing fluid production through natural or induced fractures. Details of the present-day stress, magnitudes, orientations are required to resolve these issues within an individual reservoir scale. However, thinking about regional exploration, the knowledge of maximum horizontal stress orientation would be an important first input. Despite the plate scale correlation of maximum horizontal stress orientations with plate motion, numerous high-resolution stress datasets, particularly those from sedimentary basins, they indicate that local maximum horizontal stress orientations vary between fault blocks. They can be highly perturbed from the regional stress regime. So the primary objective of first phase of Project InnerSpace, its tectonic portion, is to determine which fault blocks globally contain maximum horizontal stress data and which do not. Second case has a potential to increase the risk around an individual geothermal project. Project InnerSpace, namely its first phase, as you might have guessed, represents such a regional exploration for geothermal systems. And this study is one of its sub-projects. It focuses on high-level structural architecture of Africa, Asia, Australia, Europe, North America, and South America. And also focuses on division of those continents into fault blocks, and fault block division into blocks with available in situ stress data and blocks with not available stress data. We are using an ArcGIS platform. And our output data are our input data are standardized tectonic maps, which were introduced by Paul, and world stress map data, which I just commented on. We were looking at world stress data input. Now I can just quickly give you one of the examples. This one even got published by Paul, Doug, and others. And it's a standardized map. It contains fault patterns, any evidence of magmatism, and also facies of upper crust. With this, we are interpreting this map into main fault blocks. Why would we even worry about fault blocks? So let me give you an example. Actually, two examples. One of them is Sea of Galilee pull apart, surrounded by Galilee Mountains and Golan Heights, these three images. And second example comes from Rio Grande Rift. And here we can see bounding faults, and they divide this profile into fault blocks, similar to those we are interpreting. Here you can see location of aquifers. They are divided by aquithards. And it's really geometry and size of these fault blocks that controls maximum size of different geothermal fluid flow systems. Like this one, topography-driven fluid flow cell is controlled by size of this fault block. This compaction-driven fluid flow cell is controlled by the size of this fault block. And this buoyancy-driven fluid flow cell is controlled by size of this fault block. I wish it was that simple. As we can see from this example by Michal et al. From Rio Grande Rift, development of fluid flow cells could vary during the tectonic history of particular tectonic feature. This half-graben thought that it will be a single half-graben controlled by this normal fault, and it would be evolving. So it started with recharge era in its footfall, and then discharge was on the opposite side of this half-graben. Well, during the development of this half-graben, some internal normal faults picked up their significance, and eventually they become fairly dominant and divided former single half-graben into two. It resulted into significant shrinkage of initial large topography-driven fluid flow cell into its 50%. Another example how important is to understand tectonic history and how complicated its relationship to individual elements comes from a region with a Southern Trough in the north and Bay of California in the south. There is a system of dextral transforms with the pull-aparts in between. They become more mature, eventually become spreading centers. However, there was also deformational focusing that resulted in abandonment of these two pull-aparts and activity of these two. When we compare it with distribution of crustal thickness, we can see that Wagner-Consang has much thinner crust than this one. And that's usually the case. The problem is that there is quite a number of geothermal fields, and we know their thermal properties, and they don't seem to really worry about crustal thickness. So they are not directly correlable with the crustal thickness, and therefore not by conductive component of heat flow. So that's a lovely example why it also matters to do regional homework and understand how it affects other play concept elements, not just the heat source and not just its conductive portion. Another example comes from Basin and Range Province, and we are looking at the ArcGIS map. It was composed from data from these multiple databases. They are all abbreviated here. As a result, we can see quaternary faults in black. We can see thermal springs in light blue, and we can see volcanoes and volcanic vents in red. We can also see active geothermal sites, even including commercially producing reservoirs, geothermal systems in green. When we compare it to a surface heat flow map, and let me make a quick correction, it's in milliwatts per square meter, we don't see those geothermal systems directly correlated to surface heat flow maxima. So again, it's not just a heat source, and it's not just its conductive portion that controls their location. There must be other components, convectional component of a heat source, fluid source, reservoir, migration, caprock, other elements making up for apparent handicap. And I guess it's time to conclude. So our study focuses on assessment of global regional scale fault blocks and in situ stress. And we will deliver improvement compared to other available datasets, standardized unified system of ArcGIS-based tectonic maps, novel upper crustal division into main fault blocks, and novel standardized map of in situ stress regime correlated to fault block maps. Thanks a lot for your attention.